Hello everyone and welcome back to ATPeak Open Source AR Talk Series. Our guest today is Sachin Guruswamy. Sachin is the computer vision and robotics engineer at Luxonis. He focuses on improving device calibration, adding new on-device vision capabilities, and making DepthAI platform more accessible and reliable over ROS.
Okay, speaking of DepthAI, Sachin will go over what is DepthAI, a bit more about Luxonis, the sensors, and about some demos and live also actually some live examples. So super excited about this, and yeah, Sachin, go ahead, please.
Hey, hello everyone. My name is Sachin and I work at Luxonis, like Alex mentioned. So today we are going to look at like what we do at Luxonis and how you can exploit and how you can use and start getting started with DepthAI. So today's agenda is, like I mentioned, it's why DepthAI and what is the DepthAI OAK platform, getting started with it, and I have some live examples for you to try out. And we are also going to look at how robotics and XR can be done on DepthAI. So let's take a look at why DepthAI. At Luxonis, we started with the idea of building our device which solves health and safety problems. But at that time, we tried iterating and we realized that there is no single device that is capable of being embedded performance, spatial AI, and CV, which led us to building the DepthAI OAK series. So in DepthAI, we have basic three models right now. One is OAK1. OAK1 consists of a 12 megapixel of RGB camera, and it has the ability to run most of the AI models, which can be converted into open window format. We can do feature extraction, motion estimation, and tracking. And when you go to OAK-B, it has the same 12 MP RGB camera, but it also consists of two mono cameras. So these mono cameras helps in the stereo estimation along with all the other features. And OAK-D Lite is the smaller version of OAK-D, which has less resolution compared to the OAK-D in terms of the stereo sensing. So what is the capability of estimating the depth alongside doing the AI and other CV platforms enables us to obtain the 3D position in the world coordinates of the detected objects, features, or semantic labels. This is going to help in the activities like using your arm to pick up an object or segregating tasks or navigation or in localizing yourself in a 3D world for like the VR or AR headsets. So how does the OAK device is able to do all these things? How is it able to do unlike the other cameras that are out there? The reason why we are able to do this is because it contains MOVDS MyRedX inside it, which has a dedicated stereo depth hardware, which is capable of doing 120 FPS at the 1280 cross 800, which enables a really good depth sensing even with the passive stereo cameras. And it has two AA accelerators, S36 plus CV accelerator, which are called shapes on the MyRedX. And it consists of two small CPUs, which are able to manage this all other accelerators that are inbuilt into the device. Another thing that's missing in here is that it also contains an hardware product, which enables the motion estimation. We will go over in the examples of what exactly is the hardware too. So here are the other products of the Depth OAK. So these are all contains the same cameras, but it changes in the features. For example, now OAK-D and OAK-1, they are all USB based, which are connected to your device over USB. This is the OAK PoE model, which is connected over the power over Ethernet, and we have an IoT with 45 millimeter of distance of the stereo setup, which enables detecting at the lower distances, which is I think 0.12 centimeter. Sorry, 0.12 meter, not 1 centimeter. It's 0.12 meter, and it also consists of ESP32, which enables serial communication without having to have a CPU or a host along with your device. So you can build a standalone device which can run on its own. And we have OAK IoT 75, which is same as OAK IoT 45, but 7.5 centimeter is the baseline, and which leads to somewhere around 0.3 meters to 10 or 11 meter depth sensing accuracy, and we have OAK FFC 3P. This enables you to building your own customized version of it, version of your stereo baseline. The reason why there is different baselines is because if you take a OAK IoT 70, OAK 75 millimeter off the baseline, you can go minimum of 0.35 and you can go till 10 meters. But if you take 45 millimeter of the baseline, then you cannot actually go for the 10 meter. The maximum will be somewhere around 5 meter. The accuracy reduces as you go, as you start detecting the further objects. It's the drawback of the stereo systems. And as of the passive system, we have normal HOOKD as an issue with detecting the area with no texture pattern. For example, you can see this all white background. If you give a complete white background, OAKDs fail to detect it. That's where OAKD Pro comes in, which comes with a IR projector, which adds the texture to the images, which enables getting more accurate depth with where there is no texture in the scenery. So you can start with your you can start with DepthAI with just 4 simple steps. One is running the installation dependencies. Then you just clone our DepthAI and you install the requirements from the Python in the repo, and then you just run your DepthAI OAK. Let's just simply go over it right now. So I already just cloned it. Let's Python install requirements. And just here is an OAK, which is connected to a tripod, and here I have a OAK light, and there is an OAK1, just so that you know the sizes. Let me see. Yeah, this is an OAK IoT, which now comes in a case. So now that installation is finished, we just run Python 3 DepthAI demo. So if you see here, it starts with a RGB, which is currently running a people. There's a mobile net SSD model here. Here it can detect me, and if I bring in a water bottle, it can detect a water bottle. And if I change here from color to depth, we can see the colored version of the depth pretty much. And you can see the 3D localization point of how much distance I am standing it from the camera. And this is like the basic visualization. And you can see this is the left and the left camera of the stereo. And there is right camera. And we have rectified left and right. The rectified left and right are the modifications. That's a tiny small rotation that we do to the left and the right stereo cameras to align them in the same line, because we are converting the stereo system to normal stereo case where pixels that are matching are supposed to be in the same line. That's epipolar lines, so that it can the search for the related feature becomes one iteration instead of 2 iterations. And apart from that, you can also have the custom camera settings here. You can change the FPS resolutions of the left and right camera. And there is a recording option where you can set the record or what you press in the record, and you will set the directory and it will start recording. And as of the depth, there is different types of filtering. There is subpixel and there is the LR check. Subpixel will enable it 32 different levels between each pixel. So if there is a pixel 1 and pixel 2, there are 32. It computes the disparity at the 32 different in the middle and tries to find out the best of them, and then returns you the best with the best confidence. The LR check does the stereo from left to right and the right to left, and then compares it which has the better version of which has the better output by comparing the Euclidean distance between them, and then chooses the one based on the LR threshold we have here. So the if the lower we go, the better it will be. And there's extended disparity. What extended disparity does is that it gets the full stereo and at resolution of 1280 cross 800, and the crop version of it, which is 640 cross 480, and it does 2 times stereo on both of them and combines the result into one, so that it can use the depth at the closest region, which is because if you do just 1280 to cross 800, then minimum depth you can get it on 7.5 baseline is 0.6 meters, but if you do the extended, it will go to 0.3. So let's enable subpixel and LR check and set the confidence 170 and change it to depth, and let's reload it. Yeah, what you are saying now is that little bit of lower confidence such that it will remove, because I set the confidence to 177. It has to be, it considers it as it needs to be very accurate as the higher confidence. Sorry, lower means the higher confidence here. So it will check only show that results. So to change that, you can just increase it, then it will come back to the where it was before. And LCR threshold also does the same effect here. See by sliding it here. It's the only reason why you have to apply reload is when you enable these things. Let me disable the extended here. So now when I check is enabled, so that gives us even more better. Okay, so that's pretty much what the demo does it. But let's go on how this demo was implemented, like how you can write your own custom pipeline for this. So how is DepthAI built? DepthAI is built in the form of node and graph-based pipeline. It consists of 3 different types of basic type of nodes, which is pre-canned hardware accelerated CV, AI, or special functions. It contains a script node, using which you can write a small Python function to do some mathematical, like to find a tan angle, or to add some, if you get a result from the object detection, which are normalized, you can write a small script to unnormalize it and then feed it back to another node to modify it, to rotate it. So that's the purpose of the script nodes that we have added here. And OpenCL is more like a custom node, which the user can write their own node in OpenCL and wrap it and feed it into the device. That's the custom node. There is one example here. I think I forgot to mention here. I will share it after the session. So those are 3 basic modalities. And going back to pre-canned hardware nodes, there are like 10-15 nodes. One is like mono camera node, stereo node, color camera node, feature detector, mobile net, neural network, YOLO detector node, YOLO special net detector node, and edge detector node. And there is SPI nodes also, which is not the scope of this. I will go over them right now. Let's take a look at how mono camera node is implemented here. So let me clone it. So all these examples and the codes are open source. You can just go to github.com/Luxonis and you can find it DepthAI Python, DepthAI code, which is in C++, and DepthAI, which is like a demo example. So let's look at the mono preview example. So this, once you import the DepthAI, you will create a pipeline, and in that pipeline you will just create 2 mono nodes. One is for left and one is for right, and we have node xlink out node. Xlink out node is the node that connects from your device to out. So whatever is coming connected to the xlink node will be fed to that device, which will be collected as a queue. From the queue, you can read it and visualize using OpenCV or other visualization library that you prefer. So once you define these 4 nodes, those 4 nodes are initialized, and you assign the stream, what is the name of the stream for the xlink out, so that you can identify which one is coming from here. And for the mono left node you created it, you assign which camera socket it is. That is, we have three: left, right, and RGB socket. Now, for left we are assigning left, for right we are assigning right, and we have sensor resolution of 720p. And for this one we also have the 480p. We'll see that next. And for the right we will set the 720p, and we will connect it to the output of the we will connect the output of the mono cameras, which are like the drivers which runs the cameras, and connect it to the X link out and right, which will, like I said, which will feed to the device. So then we will initialize that pipeline with the to the device, and once it sends to the device will get the all to set the pipeline and enables only the necessary hardwares, and we start running them. And once you start running, you can just get the queues of them. And we have get and try get. Try get is just unblocking, and you can set the size of the queue that you can hold on those. If you have something like Raspberry Pi which doesn't have a lot of memory, then you can set it to smaller queues like 4 or 5. Or if you have enough memory, then you can just set it to 30. That shouldn't be a problem. So yeah, and we will once if they are filled with the data, we'll just show them using IMShow. Let's just run the example. So it's in the Python examples mono cameras. Right, so Python 3 mono preview. So what you are saying is like left and right at the resolution of 720p. So that's basically it. It's a very simple example. So let me just make a modification to see the 480p here. So the 480p just changes to 480p. So there are two functions. Once you get it in right, there are functions like get data and get CV frame. Get CV frame is an integrated OpenCV version of it. So you will just directly get an OpenCV base frame so that you can just deal with OpenCV. If you don't want OpenCV, you can just get our customized image frame, which contains the raw data, which you can load into other libraries like PIL images. So now that we have changed it to 480p, you will see a smaller resolution of that. So now you have seen how the left and right mono nodes are defined. Let's connect. Let's see an example in which these nodes are connected to the stereo node. So, like you saw in the previous version, you are seeing here is the mono nodes left and right, and we have created a stereo node here, and there is only one X link out, and it's named Disparity here. You can see there is a left is at 400p and right is at 400p. The reason why we have 400p is because we have a light resolution, OAK light, whose resolution is 400p. That's the reason why it's 400p. But if you try to set the OAK at 400p, it will default back to 480p. Sorry. So once we set and in the depth, we are setting the initial confidence of the initial confidence threshold, which we are setting here to 245. We can set it anywhere between 1 to 255. 255 would be the very liberal. 245 is kind of what we find optimal for depth visualizations and usage. There is some noise. If you want to convert into point cloud, you might want to go to 210, which gives even less noise for the point cloud from the point cloud perspective. And we have filters like median filters, which can set it to 5x5, 3x3, or you can set it completely off. Completely off means there is no filtering on top of it. That will give you very raw data, which will be more flickering. And this will enable the LR check, the one I explained before, and extended and suffixed, which are all set to false here. And we are connecting the output of the mono left into depth in left input. I mean, depth is the stereo node, and mono right to depth right input, which is stereo right camera. And we are getting the disparity output and feeding it out of the S-Sync out. And so the only output you're going to see here is only the disparity output, which is for visualization. We are applying a color map here. So once we get the frame of the disparity, we are converting it into uint18 because apply color map only wants uint18. event date, sorry. So yeah, let me run this and show how it looks. Let's do that. So this is the disparity color, which is changed for visualization. This left side is the one which is an actual disparity, how it acts coming from the raw value. So this is in event 8, if I recall correctly. So what do we want to change in this example? So let me add the outputs for the RGB left and right also here. So we add 2 more nodes. Let's name XR left, XR right. And we need the same for the left, right. And we need to name this to left. So now we have defined the X-link out, which feeds back to the device. Now we need to connect the output of the left and right to the visualization. So what we need to do is mono right out link of XR right input, and we need mono left XR left input. So now that we have defined the outputs here, we can add 2 more queues, which will be named with the left and right name that I gave to the X-link out stream name. Name it Q left, Q right. Now we need to get the frame here. Left equals to Q left dot get. So instead of get, and so here is a get frame is more of a raw frame. So we will just get the get CV frame in value dot get CV frame. And now that we have both frame, we will just have to show this. Left. Just got to push this right. So that's it. I think we should be able to see all the images now. Let me see. Okay, so let's see frame as, let's see. Okay, I think if I missed the name. Q. In that. Oh. So this is supposed to be get first to get the frame from the queue. Then I need to convert them into the get CV frame. So now you have the disparity color left, right, left, and the disparity. And let's do one more change here. Let's change this resolution back to the 720p. 720p. And what else? So, and let's enable the LR check and subpixel. Sorry. So you can see the LR check threshold is not really set well. So when I go closer here, you'll see a lot of like speckles, which is like there is no good depth data here. If I come all the way back, you'll get really well-defined, more accurate subpixel version of it. And if I enable the extended here, then you will be able to get it like a closer version also. Let's see extendeds. So right now, I don't think subpixel will work with extended. So let me set it to false and set this to true. Let's see, now the closer version is better because extended uses from the smaller resolution and the bigger resolution combines and gives you a better result at the closer depth. Okay, so now we are done with the serial example. Let's see what's the next example. So, sorry. Let's see, yeah, my bad. So, let's go to mobile net. So let's see the mobile net. So let's run this on the RGB camera one. So when you come to the DepthAI Python, I need to run the installation because when I run this, it will install the it will also download the models that are required here. So I should have done this before. Sorry, my bad. So while this downloads, there is a GPS based visual interferometry. Let's take a look at the video of it. Yeah. In this video, one of our competitors use the feature detected from the camera, which is runs on in-device camera. Using those features, and the IMU, they created visual odometry and used with the GPS. So you can see that the GPS is lost here, but the camera keeps tracking from the VIO. But you can see that the uncertainty keeps increasing around the blue point, which is like it doesn't know the exact position, but once it gains the GPS back, it aligns back to where it was. And they did this on the post processing where they combined it back into the version of one. That's one thing. Okay. So yeah, these are the other projects. These are some of the projects that were done on this. So bottom one is the using the turtle bot. Sorry, my bad. Bottom one is a turtlebot one in which the area was mapped using LiDAR before and then uses the DepthAI to navigate from point to point. And the top right one is one of the robots that was in again OpenCV competition where they have mounted an OAK here and an OAK here. The bottom OAK will be is being used for localization and mapping. And the top one, they have a voice commands where they give the voice command like, okay, can you drop this bottle to the hall? Then it will be scan the bottle, and once it's placed on the right, it will take to the person who is sitting in the hall, and it tries to search for that guy. So we'll play that video through next. Okay. we'll come back to the video later. So yeah, let's go back to mobile net. I think mobile net.py. Okay, so this is a mono mobile net which is running the mobile net detection that we saw in the demo example on the right camera. Let's do this on the RGB one. So you can see there is a person. It doesn't detect the cup, it seems only for times. Let's go over the code of this. RGB mobile net. So we have recompiled blobs that are available for you to download from the open model 2 or from our repositories. We have OpenNet SSD, we have some segmentation networks, we have YOLO V3, YOLO V4, I think, and Tiny YOLO also. And we have post detection, we have an ant tracker. These are not available on our website. We'll share you guys a link later. So this blob will be fed to the device. So once you return the results. Here we are setting a color camera like the mono camera which I said before, and we have a mobile net detection network specific for mobile net, and RGB output and an NN output, which are basically an X-Link out output to connect to the host. Next, you will set the preview size. The preview size is the size that you're going to set and feed into the mobile network. So there is a way to, so you can set the preview size. So it will resize the image from 4K or 1080 that you have set and resize it to 300 cross 300 and crop out to avoid any squishing of the image. And then it is set into then it is passed into, where is it? Yeah, NN input. NN node is the mobile net detection network. And you set the confidence to 0.5, so it will only give the results which are above 0.5. Here we are setting the path of the blob. That is more like the weights that you are passing to the for inference. Sorry. And you are also setting the number of inference threads. So you can assign the number of shapes or the NCU that it can use inside the device. That's the allocation. So if you are running other tasks, then you need to keep it to the minimum. Okay, so and what this pass-through does is that, so okay, if your detection is a little bit of a heavy model and it's taking too much time, and then if you just directly get the preview from the camera node, they might come off sync. So you might be receiving the RGB frames faster and the detections later, so that if I'm sitting here and I move out, and it will still be sending the old frames where I'm sitting here detection, and so it doesn't look right. So for that we have a pass-through feature which takes returns the input frame along with at the same time as the detection is done. Once the detection is done, so once you have both the detections, you as usual you will get both the frames, and before displaying the detection you have gotten will be normalized to 0 to 1. So you will pass the resolution of the image that is used, and so that you can recover back the original size of the detection area. So that's what's happening here. Now you get as usual you get the frames here, and once you get the RGB value, you will get the frame, and for the frame you will set the FPS. For that, we're just using a normal counter. On top of it, here is the NN detected NN detected detections. So you collect the detections, and for that you will which are assigned to the display frame, which is like global variable within the with statement. So it's used in detection here to put the rectangle and the naming of which object it is from the labels created here. That's pretty much is what MobileNet node does. So you can integrate it with the RGB camera, left camera, or right camera, or you can do it for all three. So that's so. And next is mobile net spatial node. What spatial node does is that it gets the detection here, and then we will set certain resolution, and then pass it to the stereo. Uses the depth from the stereo node and gives the average output at the center of the box, so that we kind of get an idea of where the object is. For example, if I'm sitting here, you get a detection square that I'm a person, and it will also show I am sitting at distance of this much from the camera. Let's take a look at this. Those spatial detection, spatial mobile net. So we'll take an similar mobile net node here, mobile net globe here, same labels. We will create a color node. We will create a mobile net detection network. Instead of mobile net detection network, we will create a mobile net spatial detection network. We will need to create a mono cameras and a stereo camera. And for RGB output, we will create an NN output and X out bounding box, which is like a smaller version of the bounding box. I will explain it once when I'm running this. So as usual, we'll set 300 to 300 cross 300 for the image size for the mobile net. That's the input that the network expects you to give. And we are setting the camera resolution of the RGB to 1080p. Sorry. And we have 400, depth is at 400p, which will default back to 480p. And we are setting the confidence for the stereo node. So the interesting point comes here is that in the spatial detection, once you set the you set the confidence threshold for the object detection. But what is the set boxing scale factor? Okay, set box scale factor is like if you are there's a detected object of the size like this, the sandbox scale for text confirmation, it will get the 0.5 version at the center of it. This 0.5 version of it is sent to the collects the depth of the image at that 0.5 box in the depth image and uses that part to get the average out or get the maximum or minimum of the depth from that. And it also we can also set like the minimum and maximum threshold that you need to get, because to get, so when you are filtering out all the depths, there might be some zeros which are actually not valid. So to avoid them, you can set what is the minimum threshold you are setting. So you can set the minimum threshold so that anything below that will not be considered in calculating the average or the minimum or the median of the area. So that's what this tree does. So then you connect the mono output stereo node, and I already explained what the pass through does, which is causing the RGB node with a spatial depth that NN detections that we have received, and we will connect the stereo depth output with a spatial detection input network. Okay, so that's how the pipeline is defined. So once you get the depth, it's just the rest of it is the only RGB visualization going on here. Let me run this. So, okay, this is the preview output from the RGB camera, in which it's detecting me as a box, which is of this square, which is like this square. As you can see, the square on the depth is like off of it, because we mentioned here the threshold is 0.5 here. This is the 0.5 threshold, and it is trying to get the best output out of that region in that 0.5 region of it, which you can change it your own customization value status. Yeah, and that is being used to give out the depth which we see, which is like 600 to 700 meters. So that's something different. And you can play with the depth resolution to get a different accuracy based on the way I told about setting the confidence threshold and the LR threshold. Now, since it's using 460, it is able to detect at the closer, and if you use 720p, then again you have to enable the extend disparity to detect a personal distance in OT. And if you are using the OBD IoT 45, then you don't need to do this. That's specialization. So next is edge detection. This is a very simple node. So in edge detection, you can see that we just created, let's see, which is, okay, edge detect. We have just created all three camera nodes here, mono camera, two mono cameras, one color camera, created three edge detector nodes, and created four outputs, one for each of them, three outputs, X-Link outs. Note that this is the X-Link in, which allows you to feed from the host to the device. So this is like a configuration mode that you can change. Sorry. This can be also used in the camera nodes to set the exposure or change the focus settings if you want to do manual focus. What other features? It applies for color camera and the mono cameras, but mono cameras are global shutter, so there is not much difference. So focus is only applicable for the RGB cameras. In this example, this config string is used to send the configuration of the sober filters that's used for edge detection. And once the cameras are ready, like before, we just connect the output of the cameras, all the three cameras, to the input of the edge detector node, and the output of the edge detector nodes are connected to the X-Link outs as usual. We just get the output of three of them and just do the IM show. And as the config input that that can be used on this, which you can change on your own to a custom version of it to get a different type of depth. So let's see both versions of it right now. The best part is all of this is completely running on the web, so you can just run it on top of Raspberry Pi. And if you are having one or two stream output, the load will be very less on the Raspberry Pi. Right. So this is the output from the image. So let's let me see. This is RGB, I think. Yeah, this is RGB, and this is from the left camera. This is from the right cameras. And let's change the filters here. Let's see one. Both of the filters. So by change, but the other filter there is more of a noise. This one is very less noise. So yeah, you can play with your own sober filters to get the kind of the effect that you want when you are doing this edge detection. That's pretty much it for the edge detection. So next is the feature detection. So the feature detection that are done on the OBD are arrays and let's see. We have the sheet Tomasi and the arrays filter. Sorry, I forgot that. Okay, so this is a little bit of a complicated node comparatively, but this example is really simple. We have different configurations for this stack setting, which arrays Thomas, or then you can set the same node is easy to set the hardware motion estimation accelerators, or there is another one which is optical flow. Lucas optical flow is also the threshold you need to detect the corners, how much to be for the shitomas. And there are some other functions which you can play around for the optical flow and how much of hardware that you can assign. That's all of this is configured depending on how many neural networks that you are also running in concurrent with it to optimize for the best FPS, depending on that, how much FPS do you need. So let's you created the mono left and right, which are mono cameras, and we will create a feature tracker node. These are all X out except this X link in, which is a configuration input, which we will see. Which will be used to choose the Harris or Shito marsh. So yeah, these are all the X link out nodes. Naming to get the data queues, and you'll be because since we are using it as a feature detector, we are setting the motion estimator as false here, and the cameras are set it at 400p resolution here, and we are setting the output from the feature tracker left and right to the X out tracker left and right, which are the output queues for the host, and we're getting the initialized configuration here, which so that we can change it later. And this is just it. So we get the image here, we get heat of the this is an input left and right image, which we are doing in pass through so that it comes in sync, so that it looks like both so that we can get both at the same time. If it's in out of sync, if currently this one doesn't take much resources, but the other one can take a lot of this, so pass through is the better way to get both of them at the same time. And all these messages are time-stamped using the monolithic clock from the C++, and which we have also implemented a function for it. So it will be in sync with your system timings, so you can use it in other APIs too. So okay, what drop features does is takes the features and where the location is, and iterates them and writes a circle on the images, which the frame you receive from the pass-through node of the left and right cameras. Let's take care of it. Yeah, you can see that it's pretty quick. Currently, I think it is running Harris filter. As you can see, there is it's charcoal, so it kind of gives like so many corners there from this distance, and same applies for this keyboard. And let me change it to sheet honors. So it's hard to say the difference, but I feel like it's less comparatively. It's pretty much the same. So yeah, you can use this detected corners and use it in other project, which you can build something on top of this. You can just use it for you can use this for corner detection, and then if you see the corner detected, then you can use it for some registration purposes too. But these are not ID; they don't have an ID. But let's go to the feature tracker example, which consists of IDs. Okay. So here we use the same node, but instead of setting the motion set here, we set the set motion estimator as false, which is default enabled, which is the case in this example. So let's see the pipeline. It's the same. It's the same left right. It's the same feature tracker. It's the same one X link X in, which is giving back to the feature node, and rest of it is 10. And we are assigning the hardware resources here. We are assigning 2 shares and 2 memory slices. By default, the least amount of this is the default amount. With there are 36 shares. I'm not 100% sure, but I think we have 12 or 36 shapes in the MyRedex. So if they are just sitting around, if you're not running any other algorithms, you can just assign them here. So once you get the features here, we are assigning to the window name, and the features are added to the track feature path here. So what feature path is like each of the IDs are assigned. So we will check the current ID, and if it is already there in the previous ID, then we will keep appending them depending on how much length for visualization purpose, how much length longer you can see for the visualization tracks. And in this here, we are also, if there's a hold ID is not there, then you drag new IDs that were detected, you will remove it out of the tracking queue. And these are again use draw feature is used to draw a circle and draw a line around it. And there's a tracker to determine how much longer that track path length should be. So this whole extra part is just for the visualization purpose. So in short, you will just get, let me show you. Yeah, once you get the track features, you get the track features object. The track features objects are passed here. And this feature contains an ID and an XY position of where it is in the pixel of the image. So that's all you need for the next steps. So let's look at that. So now you can see that there is a track path. Currently, it is running the optical flow, for example. Okay. So let's see if you see the checkerboard. It looks like better than seeing it at me and moving the camera. And here you can see the track duration, which is it only tracks for 10 frames, and then it updates it to remove them. Let's move this all the way to 30. So that will create like a lot of longer effect. So what you can do with this is that you can use this feature as detected, and since they are already ID'd, you can use it to calculate how visual odometer using this. And the device also comes with an IMU, so you can get the motion from IMU also and use this to create your own visual odometry on top of it. So all you need to do is once you get that movement track to IMU and movement through visual images using the track features, you can use it to run the visual odometry using the let's see least square method or some other robust methods that you can think of. And so this is optical flow method, and if I press as we change to the hardware accelerated method, which is kind of pretty much does the same thing, but it doesn't use the shapes, but as a dedicated hardware which can does the same thing. The features is extracted. The features in the hardware detected method is an extracted version of our features, but it comes with an ID, but it doesn't come with a descriptor. That's the drawback of the hardware as a tech. And in the next steps, we are actually working next year. I think in Jan we are going to start working on implementing a visual odometry node inside the device so that you can just get the poses repetitively instead of the features and doing it on device. Sorry, on out of the device, getting the feature from the device and doing the visual odometry out of the device. It's some of the basic all CV feature examples except the IMU node and segmentation. So you can try, we have those examples in those examples in the DepthAI experiment. There are a lot of examples here. So as you can see here, we have a gaze estimation here. As you can see, you can see where the person is gazing here. And we have a point cloud examples. We have a Deep Lab V3, and we have other custom models. And there is face recognition, there is face mesh, emotional detection, efficient net. And if you go to docs, you can find other use cases. You can see the pose estimation part one, and there's hand tracking. So this was an hand tracking from one of the users who used hand tracking and created examples like turning on the light based on the fingers recognitions and stuff. And you can see human safety machine license plate, hand detection, and the sign language detections, and many more. Let's go back to the demo. And I already went through a little bit of this. Okay. Let's take a look at the example. Went to the Chinese visual odometry. So this is the navigation demo of one of the users. Like I said, they have the navigation part in two cameras, one for navigation, one for neural network and detecting what the user is doing. So she's telling that to take the bottle and give it in the hall. So it's going to go closer and she can place it on the tray and then give it to the guy in the hall. So one thing I'm not sure is that if they map the house with the Hobby, I'm not sure about that, but they are definitely doing the localization using Hobby. There are only two Hobbies. Nothing else is there on there. And one other thing is we're also introducing OP wide cameras. With that way, you can eliminate one of these OP and just use one OP which gives very wide field of view of diagonal 140, I think, 140. Yep. So now it has reached the point, but it's searching for the person whom it has to kill. And they're also running a face detection and recognition. So it detects who the guy is and so that it can say Jim take the bottle. That's one example. And another interesting example that I was VR laser tag. So what this user did was that he so what okay, so he used the Oculus Quest along with the two OPDs. So he placed the two OPDs in a standpoint. Let me share. Yeah, this is first of all. As you can see, he created his own virtual environment. So, so in this environment, he placed the two hookties on the other side so that it can detect the whole environment. And he used April tags to detect all the walls and object detection models to detect the models and what distance they are, and used them to create a virtual environment. So he just for the so yeah, you can see the two hookties how he plays. So using that, he created a virtual environment where all the bound edges will be like these boxes and all these other objects that are detected in the room will be as these blockers. That way it's kind of a more of a mixed reality. So that way he doesn't have to stay in this dedicated region to use his VR headset. So yeah, that's what this example is. So you can try. I'm not sure if they open source the code, so yeah, you can try it out. And one other thing is currently in this example, he ran the April tags on device, which we recently implemented on device also. We will be moving it to mains. That way you can do April tag detection and post estimation on device also. So if you would like to buy an OP or OP Lite or other our products, you can go to our Amazon or our Luxonis.com. You can buy them. And we are selling a OP Lite at a discounted price on Indiegogo, which has been for some time. So I think there's only 13% offer is left right now. If you would like to get one, you can get a Lite there. Lite is pretty much the same as OP. It just doesn't have IMU and stereo resolution is 400p. That's the main difference. And if you already have a device and if you want to start building, you can just go to logs.luxonis.com. You can see a lot of examples. And I forgot to show the details of the nodes. You can go to the API. You can see in detail explanation of how the device can be initialized, pipeline, and each node's explanation, how each nodes can be implemented, how they can connect to other nodes, and in detail how it is implemented on device. For example, stereo node. These are all the different outputs. These are the input configuration that are available and how this whole stereo node works, how many different types of configurations you have. So you can all get it on our docs. And if you are stuck at some point and if you're not able to figure it out, you can just join our Discord community and just ping us, since we are globally in Europe and US. So then somebody will be there to help you right away. Thank you.
Oh, thank you, Sachin. It was super cool. We really enjoy it. Definitely our audience enjoyed it as well. I have a couple of questions for you. Yeah. So, oh, 1 second. It's just maybe I just switch it back between us. So yeah, one question is like, yeah, I wanted to know, well, you mentioned just if you mention a bit what people are doing in general. I mean, you show some example, but I know that actually we are aware that actually people are doing different things. But if you want to just tell everyone what people are doing with the devices.
Sorry, I didn't quite get the question part here. So you want me to explain like what different people are doing with different things?
Some applications, like general applications. I mean, we saw some, but like.
Okay, so some applications that are being reused in real world right now is that there is a company which are working on using our device on top of these warehouse devices where they can use to detect the big boxes around the lift. I'm not recalling the exact name. I think they are the things that they use to lift the big boxes and move around in the warehouses. Those are completely being automated using Hobbies. There is another one where they are using it as a webcam, which they're using OAK, one type of device like this, but they built a custom on top of it, which they're using as a webcam and giving the bokeh effect and using AI models to detect the face and make it more clearer, brighter, or run some neural networks on top of it. They're doing one version on top of this. And let me think. There's another company who are doing volumetric estimation of the shipments. And there is a fitness tracker where they're using the wide angle cameras, and so they're using the depth and the pose detection and tracking the different types of fitness and integrated with an Android app to give them like how many reps and what they did right, what they did not, and give some feedbacks on that using AI. Let me think.
Sachin, maybe another one would be related on with some of the most. I mean, because it's a really nice API and device, and maybe the most unusual, maybe like some students or some researcher, or even you guys actually internally maybe did something a bit funny with it.
So yeah, there was I'm not sure if you guys have seen that there is a mini pupper, which is a smaller version of the robot, which they are selling it on the Kickstarter. So that was integrated where we had in the Kickstarter demo, we added dancing. Let me see if I can find it. I can show you that one. And I just recalled one more. Fun ones. Let let's see. And there is Blue Box IO, which are doing the like camera for the car, which can also do level 2 autonomous navigation using OP. And the fun one will be hand pose. There is an Ardu pilot which are integrating Hope device onto the drones, which can be used for navigation and obstacle avoidance. You can find their videos on Ardu. So let me share my screen back. So here is another video where Autopilot uses the visual follower mode using OAK. And here is a 2D representation of it. They are integrating into their MAV link. If I recall correctly, they are integrating the ESP version on it so that it can directly connect talk over ESP32 so that it doesn't require another controller to carry it out. So you can see that since it's out of focus, since it's on a drone, it is not being that stabilized. So we also created a fixed focus version for drones. One thing, and 3D visualization, and this is edge detection. This is feature flattening. And there is this Cortex version of a smart board for students to learn, where they build a scratch pad for Raspberry Pi, where they can use DepthAI and just use scratch pad. I don't know if it's called just scratch. So they are just going to put the block, use the blocks to build what the robot will do.
Yeah, pretty cool. Yeah. It's like it's really interesting to see all the different applications.
That yeah, this is the mini pupper version. I think they place they have OAK light on top of it, which I think they're writing an integration into there so that you can buy an OAK light and place it on it and detect based on the hand movement. It keeps moving around. It can command it to come in or go out, something like that. That's another example that I wanted to show, but I don't have much videos of it right now.
Awesome. Nice. Yeah, pretty nice. Yeah. So well, another questions would be the right now actually the API is a Python API, and you have also.
Sorry.
What API do you have at the moment? I mean, you have a Python API that you showcased.
We have Python. We have C++ right now. We plan to do a Java version, but not depending on how many users would be interested in it. I think there is one version of Java which third party like a student or something did that, which is open source, I think. But officially, we are as of now we have Python, C++, and ROS interface.
So you have a ROS interface.
We are doing Unity simulator version of it, which is halfway through it. I think we should be able to release it in 1 or 2 months, like more updates on it.
Yeah, awesome. Really cool. Really cool. Yeah. Yeah, I think well, we were super happy to have you here, Sachin, presenting. It was really interesting. And we're gonna share all your links and also the presentations in the YouTube video in the descriptions below. Thanks again.
Yeah, thank you very much, Sachin. And we wanted to thank all of the speakers who have been part of this first open source AR talk series. And thank you, all of you, who watched all the episodes.
Yes.
So this was our last episode for this year, but we are looking for new speakers for another round next year. So if you are developing an open source project that you think would be of interest for the community, don't hesitate to reach out to us. We are looking for new speakers, so you can send us an email at info@atpeak.io. And we would like to thank our partners for their support in this first series. And if you would like to have more info on ATPeak and the lineup we had, you can visit our website, atpeak.io. And don't forget to check the AR Talk series playlist, and you can watch there all of the other talks. See you next year.
Thank you.
Thank you for inviting me and